This is the third lecture for chapter 16 and 17. We are going to start off looking at cogeneration, which is something that is not commonly thought of, at least in the general public. It's the idea of using your generation of electricity for both, of course, the electricity, but also to produce heat. In the process of producing electricity, you're burning some type of a fuel, whether it's coal or natural gas. And of course, you're making steam, and that's turning a generator, and you're creating electricity. But you do have this heat that is produced in the process, and typically a steam. And you can use that to heat something up. So for example, in Michigan State University, they have their own power plant, and they are able to utilize that steam or heat to heat all of their buildings on the campus. So it's something that they've taken advantage of since the 1950s. And of course, it also, as you can see on the slide, it improves the efficiency of your process. So instead of just say, okay, we want electricity and the excess heat is just something that goes along with the process, and we're not going to necessarily capture that heat. Most places do not, but it is a way of increasing the efficiency of that original energy resource, coal or natural gas. In the process of making electricity or moving your car or whatever you like to look at, that process always involves some level of inefficiency. So whenever you have a transfer of energy from one source to another, even the wind, there's some inefficiencies involved, and that all has to do with the second law of thermodynamics. So, for example, in heating your home, that's quite efficient, relatively speaking. That natural gas just is pumped into your house, and you burn it right in your house to produce heat. Relatively speaking, that's fairly efficient, as opposed if you would have had electrical heat in your home. Some places do, in which you are doing something to turn coal or natural gas, nuclear, whatever, into electricity that transfers over to your house, and now you're heating up some element that is now going to heat your home. Every one of those transfers involves a loss of energy. So you can see, for example, with power plants, useful energy, you're really only getting about 35% efficiency of the coal burning, which is why cogeneration is kind of nice too, because it increases that percentage up. And this is just a rough schematic of that process, which I just kind of talked about here a second ago. I'm not going to spend a lot of time here, but you can pause it and take a look at all the guts of this. But notice a similarity with this to nuclear energy, in which we'll look at here, I think, shortly. And the process for nuclear is you're using uranium and sometimes plutonium, I believe, to do the exact same thing as a nuclear power plant. You're just heating up water. That's all you're trying to do is heat up water, make steam, and turn a turbine. The only difference is for a nuclear power plant is, of course, you're using these very dangerous materials to do that process. You're not going to have an explosion like a Hiroshima bomb in a nuclear power plant. It's just not possible. It's not enriched to that level. But of course, you could have a Fukushima in which you have an accident and then you have radioactive material spilling out and contaminating an area for years to come, or a Chernobyl accident kind of thing. So there's definitely risks involved in using nuclear. Here's a schematic which is quite similar to the one that was on the 2 slides ago, looking at the coal-fired power plant. It does the same thing. All you're doing is you're boiling water. That's the whole point or process, is to boil water to turn a turbine. Again, looking at some of the problems with a nuclear power plant is the fact that you have this energy resource which is incredibly dangerous. In the environment, it is very spread out. You're concentrating it, and now you have this waste material that, quite honestly, you just can't ever get rid of. And of course, with potential problems with terrorism or explosions or natural disasters, you set yourself up for some problems in the future. Something that's interesting for all nuclear power plants is their waste materials. are stored on site. So we have some that are close to us. It's the Fermi nuclear power plant in the Monroe area. Every bit of waste that they've ever generated in the last some 50 years is still there. Now, granted, those things, again, are very, very efficient, but every bit of their waste control rods or the nuclear fuel rods are still stored on site because you don't want to be moving those around because of potential problems that could happen. In the last 30 years or so, we've made very few, if any, nuclear power plants. There is talk on making more and some smaller ones. I've just been reading that in the news lately. Smaller nuclear power plants. They're all always very expensive to make because of all the safety considerations that go into it. So when you look at the energy, it's rather cheap, but there's a huge energy cost up front and then a never-ending cost after the use of the fuel that you have to deal with. And of course, all the public concerns and the potentials of what could happen make it relatively expensive. This is looking at the capacity of nuclear energy over the last 40 some odd years. And you can see it's been fairly constant in that time period since, I guess, maybe the last 30 years or so. So countries really have not invested a lot in this, with maybe the exception of China over the last 30 some odd years. It's been fairly constant, and countries are starting to look for different resources to make energy. And I've talked about this a little bit, that a lot of our nuclear power plants have reached the end of their productive lifespan, and just based on wear and tear, they need to be decommissioned. And we keep recommissioning them and extending their lifespan out further than what was supposed to be. And this is something that we're dealing with now. And decisions are being made or have to be made that how long can these things last without potentially having some problems. This is just looking, this slide here as far as our inputs and outputs for our energy, and showing that a lot of the energy that we generate is just wasted. It's not efficient. Some parts you really can't avoid because of the second law of thermodynamics, but other parts are just based on how we use it. We could do a better job of utilizing that energy resource. All right, fusion is the ultimate goal. This has just been in the news very recently. In Japan, they're just starting to, I don't want to say get it to work, because it's 5 seconds is not a huge victory, but they have gotten real fusion to work, in which they're heating something up to 150 million degrees, which is the relative heat of the center of the sun. Now, of course, because that is so incredibly hot, it's very difficult to maintain. But you're getting more energy out than you're putting in. So that's, of course, a very big deal. But realistically, scientists have not been able to get this to work yet. But it is the hope as far as energy production that if we ever do get this to work efficiently, it will solve a variety of problems. This is a slightly different video version of fusion. They call it cold fusion. A better name would be like a nuclear reaction. And we can talk about this in class if we have time to bring it up. It's another way of getting more energy in an output than energy on an input. But it really hasn't moved far as being a commercial product. But it is another thought of something that engineering is pursuing. These are some things that are very wasteful in the way we have used energy, and some that we still do, and some that we haven't anymore. So incandescent light bulbs are really a thing of the past. We don't use those much anymore because they are so wasteful, and we have some good light substitutes for that. Car engines are incredibly inefficient. The internal combustion engine, sometimes called ICE, and you can see the percentage on it that it's just most of the energy produced just goes off as heat. Nuclear power plants, and you can see the other ones on there as well. So anytime you're using a fuel source to create an energy, a transfer, you're going to have inefficiencies involved. Let me go back to that one. This little schematic is just showing a slight difference and just showing how whatever you're trying to do, produce some heat for your home. If you're using uranium and nuclear power plants, you're really not getting much heat on the end of the line. If you're using something like just passive solar heat and very good insulation in your home, you could be much more efficient. And there are some homes. There's one in Ann Arbor, which I saw a video on a while ago, where most of the energy for the home just comes from the sun. And it's a rather large home, but the way it's designed and insulated, it's very efficient. So it's just, part of it is just based on design. All right, this is a good place to take a break, and we'll come back with another lecture after this.